Hello everyone, and welcome to this session. We've just discussed when an analysis of variance is used, and now we want to go through the mechanics of performing a one-way ANOVA. So what we would like to do in this section are to understand how the analysis of variance procedure divides the total variability in measured data into different contributions from different sources. We want to explain how a one-way ANOVA distinguishes between the variation between populations and the variation within the populations by calculating the sum of squares from measured data and comparing the mean square of the treatments to the mean square of the error using the F statistic. And we want you to be able to determine if the means of different populations are different up to a given significance level, or for a given significance level. So again, we have the picture here of our variable, our critical to quality variable for different groups, for different treatment combinations we've been saying in the design of experiments. So this could also be, as we have here, the current process compared to other different processes. And again, we're using the ANOVA because we have more than two different populations that we want to compare. Here we have four different populations. So in a one-way ANOVA, we have independent samples, random samples, drawn from different normally distributed populations. Each population, so 1, 2, 3, and 4, has their own mean and standard deviation. And from our samples, then, we can calculate a sample mean and a sample standard deviation for each of the population, which then is our unbiased estimator for the actual mean and standard deviation of that, mean and variance of that population. Now here we're showing you can have different sample sizes. That's also possible, although in this lecture we're going to assume the sample sizes are the same. Now, often in this lecture, as I said, we'll refer to these populations' differences as treatments, and the null hypothesis here is that all the means are equal, that there's no difference. We have to prove with our samples that they are statistically different. Now, what does that mean? So here's our picture again, and if we drew, like we did in the last lecture, this idea that each of these populations, for example, here this has a certain mean, mu1, and the blue population here, if we were modeling this, would have a mu3. So the question is, are these means different? Well, what we're going to be doing here is looking at that, but also looking at the variability that each of these distributions has. And overall, considering that the overall variability is a component of a possible difference between the different treatments, and this is not a very good picture, and the variation that we're seeing within the populations. Now, I have a better picture on the next slide. Here we go again. The one-way ANOVA allows us to compare the variation within the groups to the variation between the groups. Is the difference in the means of the groups, so the variability between the groups that we show here, is that more significant than the variability within the groups, like, for example, the background noise? We have variability in each of these groups. Now, you may be asking yourself, why are we looking at variances? Why is this called ANOVA, analysis of variance, when we're actually testing means? Well, the idea is that we want to see if the observed difference in the means due to the treatments is too large to be due just to the result of random selection. There is variability within each population, and we might end up having very similar populations for the different treatments. For example, we might end up having a population that looks like this, and then for a different treatment, we've done a different treatment, but actually the population doesn't change. But there's variation within both of those. And it could be that our random samples that we take from the red and the purple there happen to give us sample means that appear very different. So the ANOVA will tell us if the difference in these sample means, taking into account the variability, is significant or not. And this is the same idea as we had before with the Z and the T-test. We calculated a test statistic, taking into account the standard deviation. Either if we knew it from the population, we could use a Z-test, or we didn't know we knew it, but we can use a T-test. We calculated those test statistic and then would compare that against a certain alpha value to see if the difference was significant. So to do this, though, we need a new statistic, and this is called the F ratio. And the F ratio is the between group variance divided by the within groups variance. And so what you see here is that the F ratio is going to get larger as this between group variability gets larger compared to the within group. So you have here this idea, then we've got to find the between group variance, a summary of the mean differences between all groups at once. That's what we're going to do next. Maybe I just make a little bit, this can think of this as noise, as random error, right? So we need to do this by using what is called the sum of squares. We're going to start by considering the variation in our data having different components. We have a component due to the actual difference in the treatments and a component due to random variation. Now, as we've done before, I know there's an equation here, but we've seen this equation right at the beginning of the course. Variance is a way of measuring the variability of our data. The way we do it, as we've always done before, is we take the difference between the individual values minus the overall mean, we square that difference, and we sum all of those differences. All of those square differences. Then we divide by this n minus 1 value, this idea of degrees of freedom. That was this measure variance that gives us a feel for how variable our data is. Now, we're just going to make one small, that hasn't changed. Nothing is new there. We're just going to do one small thing, and that is to break this up into two different parts. The numerator here, we're going to call now the sum of squares, whereas the denominator is going to be called the degrees of freedom. So, kind of makes sense. We're summing up the square values there, the squares of the differences toward the mean, and the denominator is called the degrees of freedom. Now, as we just said, we're going to take this entire variation and we're going to split it then into two components. One part due to the treatments and one part due to the random variation. So, we're going to call the total sum of squares broken into then sum of squares of treatment and sum of squares of error. And so we're going to abbreviate that as SST plus SSE. So in other words, the variation due to the treatments, the between population variation, plus the variation due to random error, the within population variation, is what is causing this total error that we see. Now, we need some data to be able to do this, and we organize this into a table. Let's look at the data that we need. First, we need to have different levels of a single factor. So, as we said, before we had only 2 levels, now we can have more than 2 levels. And we have here 8 different levels of a single factor. So, factor level 1, level 2, level 3, level 4, up to level A. This is index I. And then we have n different observations that we're taking within each factor level. So J is going then from 1 to n. Now, for each factor level, we can calculate a total value and an average value. And here, we just augment my file here a little. This would be a bar, not very clear. So we have then an average value, I have this here, for one single factor level. Here we can take the total, we sum these up to get the total, and from there we can get an average for one single factor level I. And then we can also calculate an overall average. We sum all of these row averages up and take the average. And what I just wanted to show here was that one individual measurement value would be at one particular factor level and would be one of the particular observations, or we call them replicates at that particular level. So this is the data that we need, and it looks complicated in this form, but we'll look at an example. It's not that complicated. So you collect all this data into the table. Now again, the sum of squares treatment, this SST, is related then to the variation between the rows, right? So this is this idea of SST. We're seeing if there's actual variation due to the different treatments of factor A, while within the SSE is going to be related. It's going to be related to, I can write this, this will be the SSE, the error. It's going to be related to the variation that we see within these rows. Because obviously if it's one factor level, you wouldn't expect they should all be the same. You shouldn't, Y11 should be the same as Y12, etc. You shouldn't have any differences. But we do because of random error. So, again, we want to compare the between group variability with the within group variability to see if there's a statistical difference. So we have the sum of squares total is equal to the sum of squares for the treatment plus the sum of squares for the error. And if you write this algebraically using the data from our table, it looks like this. And let's go through a few things. So here what we see is in the first term we have our overall sum of squares. Do you remember we just did it before? It's every individual value minus the overall mean. And that's this y bar dot dot. That was in the corner of the table. Now, the second term is then going to be the sum of squares due to the different treatment averages. So we have the different, this is the row averages for one single factor level here, compared to the overall mean, the y bar dot dot. And we're going to do that then, you see the sum, you do that for every single different treatment value. And in this case, we have to multiply by n because we're assuming we have n different replicates in each. So we sum up then these different squared for each of those different treatments. Now finally the error term then, which is this term, is going to be each individual value within one particular row, so compared to the average of that particular row. So we have to do that not only across all the different replicates in each row, but we have to do it for each individual row. So that's why these sums are a little bit different here. But what we're trying to do is to take into account every single bit of the variability, which we did here. This is correct. But now we're splitting it into these two components. And this is just algebra. There's nothing mysterious about this. I mean, you can go through this and go back and see that these are equal. But it's we want to be able to make sure you understand that we're comparing the sum of squares for the treatments to this plus the sum of squares of the error. We're splitting these up. Look at this again here. This is the same picture we had before. So the total error, which if we wanted to draw that, we would draw this, we'd have to combine all of these, the sum of squared total, look at the total error, but we're going to be looking at then the variation between the groups compared to the variation within the groups. Again, that's what we're doing. And now we come to the sort of the heart of the ANOVA, and this is what a computer would generate for you, because all of this is very difficult to calculate by hand. So also in this course, we're not expecting you to do that, but we want you to understand the idea. Here we have the ANOVA table for a one-way single-factor ANOVA. We need a new term now called the mean square. Now, what you see is that this is the sum of squares over the degrees of freedom, which you probably already noticed is we just took our good old sample variance. We broke it up into a numerator and a denominator. We called the numerator sum of squares and the denominator degrees of freedom. And now we're putting them back together. But this time we're putting them back together for our different components of the overall variance. So we've got the source of variation due to the treatments. We have the algebraic value of that. And we have the degrees of freedom for that, which since we have A different treatment types, the degrees of freedom is A minus 1. So the mean squares is going to be this SST divided by A minus 1. The source of variation due to the error, we also looked at that already on the previous slide. Degrees of freedom, then we have N minus 1, so each individual population has N minus 1 degrees of freedom, and we have A population, so A times N minus 1. So the mean square error factor is the sum of squares of the error over A times N minus 1. And the F statistic, as we've discussed before, the F statistic was the ratio of the variability between the treatments to the variability of the error. And that's what we see here. So these two values have to go in here. And as we said before, as the F statistic gets larger, this means that this MS treatment is getting larger compared to this MS error. And the larger it is, the more we can prove, or we see the significance of the difference between our treatments, and then we can reject. So maybe I just write that down. Large F, you could hopefully reject the null hypothesis. And do you remember the null hypothesis here was that there was no difference between the means? If this MS treatment starts getting big, then that means we will have a significant difference and we reject HO. So let's see how this works. So for example, and normally for tables, you'd just be using a 95% significance level or a 90%. And so we have an F table. Here's our F table here. This is from our book. And we have our degrees of freedom. Now the degrees of freedom, V1 and V2. So we have here V1 is this way for the numerator and V2 is this way for the denominator. So the numerator is SST. If I go back one slide, so SST, we have degrees of freedom A minus 1. So A minus 1 is V1. And maybe I'll give an example of that in a minute. V2 is then going to be the degrees of freedom for the error, which is A times N minus 1. There's V2. So for example, if we had four different treatments, right? Then we'd have A equals to 4. And this one would be 4 minus 1 equals 3. And if we had, for example, 6 measurements, 6 replicates at each level, we'd get here then 4 times 6 minus 1, which is 4 times 5, which is equal to 20. So V1 is equal then here to 3, and V2, or FAU2, is equal to 20. So from our F table, you can read this critical value. Now what this critical value means, again, it's the same idea as before. If your F observed, maybe I should write F observed, from your data is larger than this F critical, then you reject the null hypothesis. So you take your data, you calculate the sum of squares for the treatments, divide by A minus 1 to get the mean square treatment. You take the sum of squares for the error, divide by A times N minus 1 to get the mean squared error, and you see F observation less than 310 for this example. You cannot reject the null hypothesis. This means the means are the same. F observation is greater than 3.10. You can reject the null hypothesis and say that the means are different.